Imagine you're a detective, not the classic one with a magnifying glass and a trench coat, but a data detective solving mysteries hidden in piles of numbers, text, and patterns. Your job? To make accurate predictions based on the evidence you have. But there's a catch. You have to assume that all pieces of evidence are independent. Sounds limiting, right? Yet, this seemingly naive assumption powers one of the most effective and widely used algorithms in machine learning, the naive Bayes classifier. Now, here's where it gets interesting. Think about email spam detection. How does your email provider instantly decide whether an email belongs in your inbox or should be exiled to the spam folder? Or how does Netflix figure out whether you'll love that new thriller based on what you've watched before? There's a good chance naive Bayes is behind it. This simple yet powerful classifier leverages probability to make fast, surprisingly accurate predictions, even with limited data. But let's not get ahead of ourselves. What exactly is naive Bayes? How does it make these decisions with such speed and precision? And why, despite its naive name, is it one of the most powerful tools in a data scientist's arsenal? Stick with me, because in just a moment, we'll dive deep into how this algorithm works, why it's so effective, and where its limitations lie. If you think machine learning is all about complex neural networks and deep learning, get ready for a surprise. Picture this. You're at the start of a crime-solving investigation, and your toolkit is based on probabilities. Instead of assuming that every clue is interconnected, you take a simpler approach. You treat each clue as though it stands on its own, independent of any other. It might sound counterintuitive, especially if you are used to thinking in terms of intricate cause and effect chains, but this exact logic forms the backbone of the naive Bayes classifier. Now, why does this matter? At its heart, the naive Bayes classifier operates on a fascinating principle rooted in Bayes' theorem. The theorem provides a way to update the probability of a hypothesis as more evidence or information becomes available. Let's break it down. When the classifier encounters a new set of input features, it calculates the likelihood of each possible outcome based on what it already knows, then adjusts its predictions accordingly. But here's the twist. It assumes that every predictor or feature is independent of the others. This is where the naive in naive Bayes comes from, not because the algorithm itself is unsophisticated, but because of this bold assumption about independence. For example, imagine you're trying to classify emails as either spam or not spam. You might look at specific features like the presence of the word free, the frequency of exclamation marks, or whether the sender is in your contact list. Each of these features is treated as a separate piece of evidence, completely independent of the others. Based on probabilities derived from previous data, the classifier quickly calculates the odds of an email belonging to each category. Despite this simplification, naive Bayes has proven to be incredibly effective, especially in applications like spam detection, medical diagnosis, and sentiment analysis. What makes this classifier particularly appealing is its computational efficiency. By assuming independence among features, the algorithm avoids the heavy lifting required to model complex relationships between predictors. It's a bit like deciding to take a shortcut through a quiet side street instead of getting stuck in the gridlock of a busy downtown intersection. Sure, the side street might not give you a perfect view of the entire city, but it gets you to your destination quickly and reliably. But here's the question that keeps us on edge. Is this independence assumption really valid? After all, in real-world scenarios, features often have subtle dependencies that are hard to ignore. For instance, in a medical diagnosis context, symptoms like fever and fatigue are rarely independent. They often occur together due to an underlying condition. Yet, despite this seeming limitation, the naive Bayes classifier has repeatedly shown its value in a wide range of applications. How does it achieve such robust performance with such a naive foundation? And what happens when the assumptions it makes don't hold up? These are the questions we'll explore as we dive deeper into the mechanics of the algorithm. We'll unravel how Bayes' theorem works, why it's such a cornerstone of probability, and what makes naive Bayes a go-to tool for many machine learning practitioners. Stay with me, because this is where the story of simplicity, efficiency, and surprising effectiveness truly begins. Let's dive into Bayes' theorem and make it come alive. Bayes' theorem is a framework for updating what we believe in light of new evidence. Imagine you're trying to figure out how likely an email is to be spam. You already have an idea based on past data. That's the prior probability. Then you look at the content of the email. Maybe it has the word free in the subject line or contains multiple exclamation points. That's your evidence. Bayes' theorem takes both of these and combines them to give you a more refined probability, the posterior. Here's how it works mathematically. P of C given x equals P of x given C times P of C, all divided by P of x. Let me explain. P of C given x is the probability of your class, like spam, being true after considering the evidence x. P of x given C is the likelihood of observing that specific evidence if the email is indeed spam. P of C is your prior, how common spam emails are in general, and P of x is the total probability of that evidence appearing in any context. The formula balances these elements to tell you how likely something is, given what you already know and what the evidence tells you now. To make this practical, let's think about a medical diagnosis scenario. Suppose the chance of someone having a rare disease is 1%. That's your prior probability. Then they test positive on a diagnostic test that's 90% accurate, meaning it correctly identifies the disease in 90 out of 100 cases, but the test also has some false positives. It might incorrectly flag someone without the disease. Bayes' theorem helps you balance these probabilities. Even with a positive test, the chance of actually having the disease might still be fairly low, given how rare it is. This same logic applies in many fields. It's why spam filters work so well, sifting through millions of emails to predict which ones should be flagged. It's why recommendation systems can predict what movies you'll love based on patterns in user behavior. And it's why sentiment analysis can parse through social media posts and classify their tone as positive, negative, or neutral. Bayes' theorem is all about refining probabilities. It's like a lens that sharpens your view as you collect more evidence. But here's the twist. While the math behind Bayes is elegant and sound, the way it's used in naive Bayes assumes that every feature is independent, which isn't always true in the real world. So how does this independence assumption shape the way naive Bayes works? And how does the algorithm handle scenarios where features aren't truly independent? These are the questions we'll explore as we move forward. Let's keep unraveling this fascinating story. Now that we understand the foundation of Bayes' theorem, let's take a closer look at the different types of naive Bayes classifiers. Think of these as variations on a theme, each one tailored for specific types of data and situations. It's like having a Swiss Army knife with different tools for different jobs. The two we're exploring here are the Gaussian naive Bayes and the Bernoulli naive Bayes. Let's start with Gaussian naive Bayes. This version assumes that the features in your data follow a Gaussian or normal distribution. Think of a classic bell curve. Symmetrical, with most of the data clustered around the mean. This is especially useful for continuous data like heights, weights, or scores, where the values naturally spread out in a predictable way. Gaussian naive Bayes uses the mean and variance of these features to calculate probabilities. It's a great fit for tasks like spam detection, where word scores or patterns often fall into a continuous range. Now shift gears to the Bernoulli naive Bayes. This one is designed for binary or Boolean features, essentially yes or no questions. Does the email contain the word free? Does it have a suspicious attachment? In this case, each feature can only take one of two values, typically 0 or 1. It's especially effective in document classification tasks, where the presence or absence of a word matters more than its frequency. Imagine analyzing text for spam detection. Instead of counting how often a word appears, Bernoulli naive Bayes checks if it's there at all, making decisions based on that simple presence or absence logic. What's fascinating is that both classifiers, despite their differences, rely on the same core assumption: feature independence. Gaussian assumes the values of features are independent and follow a normal distribution. Bernoulli, on the other hand, assumes that the presence or absence of each feature is independent of all others. This independence assumption is what allows naive Bayes to be computationally efficient and surprisingly effective, even in scenarios where features might actually be dependent. But here's the cliffhanger. What happens when we move beyond binary or continuous data? What if the features don't follow a Gaussian distribution or can't be boiled down to zeros and ones? That's where the next step comes in, exploring other variations like the multinomial naive Bayes, tailored for categorical data. Stick around, because the journey into naive Bayes is just getting started. Let's zoom in on one specific type of naive Bayes, the Gaussian naive Bayes classifier. This is the go-to choice when you're working with continuous data, numbers that aren't just on or off, but exist on a spectrum, like measurements or scores. The beauty of Gaussian naive Bayes lies in its simplicity and its ability to make sense of such data by leveraging a concept most of us are already familiar with: the bell curve, or Gaussian distribution. Here's how it works. Gaussian naive Bayes assumes that your continuous features, given the class, follow a normal distribution. For instance, imagine you're classifying whether a patient is healthy or has a condition based on their body temperature. The classifier assumes that body temperature data for healthy people will cluster around a certain mean, forming a bell curve, and the same for people with the condition, but with a different mean and variance. These assumptions make it possible to calculate probabilities quickly and efficiently, even for datasets with continuous variables. The process hinges on two key assumptions. First, just like with all naive Bayes classifiers, Gaussian naive Bayes assumes that features are independent of one another given the class label. For example, it treats a person's blood pressure as completely unrelated to their cholesterol level, an assumption that simplifies the math but might not always hold true in reality. Second, it uses the Gaussian probability density function to model these continuous features. This is where the classifier shines. Instead of discretizing the data, chopping it into bins, it works directly with the original continuous values, retaining more of the information. The real power of Gaussian naive Bayes comes from its ability to handle data without oversimplifying it. By modeling the distribution of continuous features directly, it avoids the pitfalls of methods that lose information through discretization. This approach is why Gaussian naive Bayes is such a strong performer in scenarios like spam detection, text classification, and even medical diagnosis, where continuous data is abundant. But here's the question that keeps things interesting. How often do real-world data sets actually follow a perfect Gaussian distribution? And what happens when they don't? Gaussian naive Bayes is incredibly effective when its assumptions align with reality, but when they don't, its performance can falter. In those cases, other types of classifiers or additional preprocessing may be needed to handle the quirks of real-world data. So while Gaussian naive Bayes is a remarkable tool, its effectiveness depends heavily on how well your data fits its assumptions. This invites us to think critically about when and where to use it. Up next, we'll explore how other types of naive Bayes classifiers tackle different kinds of data, giving us a broader toolkit to work with. Let's keep going. Let's dive into the Bernoulli naive Bayes classifier, a specialized version of naive Bayes designed for scenarios where features are binary. Picture this. You're analyzing whether an email is spam or not. Instead of focusing on how many times a word like offer or free appears, Bernoulli naive Bayes simplifies the task, asking a straightforward yes or no question for each feature. Does the word free exist in this email? Yes or no. Does it have an attachment? Yes or no. This classifier works wonders when binary presence or absence is more meaningful than frequency. The Bernoulli naive Bayes classifier operates under a few key assumptions. First, each feature, whether it's the presence of a word, a tag, or another binary characteristic, is considered independent of the others given the class label. For example, it assumes that the word offer being present in an email doesn't influence whether prize is also present. This independence assumption simplifies the computations while still delivering impressive accuracy in many tasks. Now let's talk about how it handles data. Bernoulli naive Bayes utilizes a Bernoulli distribution which models outcomes that have only two possibilities: true or false, yes or no, 1 or 0. For example, in a text classification task, it determines the likelihood of an email being spam by looking at whether specific words are present, value 1, or absent, value 0. This focus on binary data is what makes the Bernoulli classifier so effective in tasks like spam detection, where the presence or absence of specific keywords can be a critical clue. What's fascinating is how well it scales to large datasets. Bernoulli naive Bayes is both simple and efficient, meaning it can handle high-dimensional data, such as text documents with thousands of unique words, without getting bogged down. That's a big reason why it's so commonly used in real-world applications, where datasets often include a massive number of features. But here's where things get interesting: the independence assumption. In reality, features are rarely truly independent. Words in an email, for instance, often appear together in meaningful ways. The phrase limited offer might carry a stronger spam signal than the words limited and offer considered separately. Bernoulli naive Bayes doesn't capture this context, which can limit its performance in some situations. Even so, Bernoulli naive Bayes is a reliable and practical tool when applied to the right kind of data. It's especially useful when your features are binary and when the simplicity of modeling independence helps you get fast and effective results. But what happens when your data isn't binary, or when you want to account for frequencies rather than mere presence? That's where the multinomial naive Bayes classifier comes in, and we're about to uncover how it opens the door to even more possibilities. Let's keep building this story. So far, we've taken a deep dive into the Gaussian and Bernoulli naive Bayes classifiers, each with their own unique strengths and ideal use cases. The Gaussian classifier thrives in the world of continuous data, relying on smooth distributions and bell curves to handle things like measurements and numerical scores. The Bernoulli classifier, on the other hand, is built for simplicity, dealing in binary yes or no questions, perfect for scenarios like spam detection, where presence or absence is all that matters. But what happens when you move into a space that's neither purely continuous nor binary? Imagine for a moment you're analyzing text data. Think about a product review where words like amazing or great might appear multiple times. In text classification tasks, it's not just the presence of a word that matters, but how frequently it shows up. A single great in a review might indicate a positive experience, but if you see great repeated 5 or 6 times, it signals enthusiasm. Frequency starts to carry real weight. This is where we encounter a new challenge. Binary approaches like Bernoulli don't account for repetition, and continuous models like Gaussian aren't built for data like this. You need something that thrives in this middle ground, a classifier that can capture and leverage the frequency of discrete data to make predictions. Enter the multinomial naive Bayes classifier. Now, let me set the scene. Think about all the real-world scenarios where frequencies dominate. Spam detection systems Don't just look for the word offer, but consider how often it's repeated across emails. Sentiment analysis tools don't just check if the word love is in a review, they measure how strongly it's emphasized by repetition. Recommendation systems analyzing product descriptions or user comments rely heavily on counting patterns in data. All of this requires a classifier built to handle not just whether features exist, but how much they appear. Here's the magic of the multinomial naive Bayes classifier. It doesn't just give us a way to measure probabilities, it thrives in high-dimensional spaces with thousands of features. In text classification, for example, each unique word in a dataset becomes a feature. Imagine the sheer scale of this. Thousands, sometimes tens of thousands of unique terms. And yet, the multinomial naive Bayes classifier can manage this complexity with speed and efficiency. But there's a catch. Just like its siblings, the multinomial classifier assumes feature independence. It doesn't consider relationships or contexts between features. In other words, it sees every word as existing in isolation. While this might feel like an oversimplification, it's a trade-off that keeps the model lightweight and fast without sacrificing too much accuracy. So how does this classifier actually work? How does it transform raw counts into meaningful predictions? And why has it become the go-to tool for so many natural language processing tasks? Let's step into slide 6 and uncover the inner workings of the multinomial naive Bayes classifier. From handling term frequencies to tackling large feature spaces, this is where we see naive Bayes shine in yet another fascinating way. Buckle up, because things are about to get even more practical and even more powerful. Data preprocessing is where the magic begins. Before any model gets to work, the data needs to be prepped, polished, and ready to go. Think of it like getting a race car ready for the track. You wouldn't just hop in and drive without checking the tires, tuning the engine, and making sure everything is in perfect condition. The same is true for machine learning. Without proper preprocessing, even the most sophisticated algorithms can't perform at their best. It starts with handling missing values. Imagine a data set where some fields are blank. How do you calculate probabilities when certain pieces of the puzzle are missing? If you're working with a customer database, for instance, you might have age and income data for most people, but a few records are incomplete. Those gaps can throw off the entire calculation. To fix this, you might choose to fill in those blanks using averages or patterns from the data, or you could remove incomplete records altogether. This step ensures the dataset is complete and ready for analysis. Next comes encoding categorical variables. Not all data is numerical. Sometimes it includes categories like colors, red, blue, green, or labels like yes or no. But machine learning algorithms can't process words or categories directly. They need numbers. Encoding transforms these categories into numbers. One hot encoding, for example, creates a binary column for each category. If red is present, it gets a 1, and all other categories get a 0. It's like converting words into a code the algorithm can understand. For certain models, continuous data needs to be discretized. This step involves grouping continuous values into intervals or bins. Think of it like organizing a bookshelf. Instead of leaving all the books scattered, you place them in neat categories: fiction, non-fiction, biographies. With continuous data, you might take ages and group them into ranges: 1825, 2635, and so on. Discretization makes the data easier to handle for some algorithms, but it comes with a trade-off. Too many bins, and the data becomes noisy. Too few, and you lose important details. Finally, normalization or standardization ensures that all features have equal weight. Imagine you're comparing two features. one measured in centimeters and another in kilometers. Without scaling, the larger unit will dominate, distorting the results. Normalizing rescales everything to a consistent range, such as 0 to 1 or 1 to 1, ensuring that no single feature overpowers the others. It's like leveling the playing field so every variable has an equal chance to contribute. Preprocessing might not sound glamorous, but it's one of the most critical steps in machine learning. It's what ensures the data is clean, structured, and ready for action. Without it, even the best algorithm is flying blind. But here's the kicker. There's an art to it. Over-prepping the data can strip away valuable information. Under-prepping can leave noise and inconsistencies that confuse the model. Striking the right balance is what makes pre-processing a skill that separates a good data scientist from a great one. So how do these steps come together in practice? Let's move ahead and see how it all unfolds. When working with continuous features, handling them effectively is a critical step in ensuring that models like naive Bayes perform at their best. Continuous data is rich with information, but without the right transformations, it can overwhelm a model or skew its predictions. This step is about refining that data, transforming it into a form that aligns with the assumptions of the algorithm while preserving its most valuable insights. One approach is binning, which involves discretizing continuous features into categorical bins. Imagine you're analyzing customer income levels. Instead of dealing with individual dollar amounts, you might group the data into ranges: low income, middle income, and high income. Binning reduces the complexity of the data and helps manage outliers, but there's a trade-off. It can also lead to information loss. If your bins are too broad, you might overlook subtle patterns in the data. Another method is normalization, which scales continuous features to a standard range, typically between 0 and 1 or 1 and 1. Let's say one feature represents a person's height in centimeters, while another is their age in years. Without normalization, the feature with the larger scale, height, might dominate the model's calculations, even if it's less important. By scaling everything to the same range, normalization ensures that every feature contributes equally to the analysis. Then there's transformation, which applies mathematical functions to continuous data to stabilize variance and make the distribution more Gaussian-like. For example, you might take the logarithm or square root of values to reduce skewness. This step is particularly useful when the data doesn't naturally follow a bell curve. Aligning the feature distribution with the model's assumptions enhances its ability to calculate probabilities accurately. Together, these techniques, binning, normalization, and transformation, are like tools in a sculptor's toolkit. They shape the raw, unprocessed data into a form that fits the needs of the algorithm, but there's always a balance to strike. Over-transforming the data can smooth out important details, while under-transforming can leave noise and irregularities that confuse the model. As we move forward, it's worth considering how these pre-processing steps interact with the assumptions of naive Bayes and its different variants. The way continuous features are handled can dramatically affect the classifier's performance and its ability to extract meaningful patterns. Let's see how these approaches come to life in real-world applications, bridging the gap between raw data and actionable insights. Naive Bayes classifiers have long been celebrated for their simplicity, efficiency, and effectiveness in solving many machine learning problems. But what exactly makes them such a reliable choice, even in challenging scenarios? Their advantages lie not just in their mathematical elegance, but in their ability to scale and adapt to different types of datasets with minimal complexity. Let's break it down. First, simplicity and ease of implementation stand out as defining strengths. Naive Bayes is straightforward to understand, making it an excellent starting point for beginners in machine learning. There's no need for extensive parameter tuning or complex architectures. The algorithm can be implemented with just a few lines of code, yet it provides solid results in many use cases. This ease of use also translates to speed. Naive Bayes is quick to deploy, whether you're building a spam filter, classifying documents, or analyzing sentiment. Efficiency in training and prediction is another hallmark of naive Bayes. Unlike more complex algorithms that require significant computational resources, naive Bayes is lightweight and fast. It excels in scenarios where quick decisions are needed, such as real-time spam detection or sentiment analysis. Its ability to train rapidly on even large datasets makes it a favorite for applications where speed is critical. Effectiveness with high-dimensional data is where naive Bayes truly shines. Think about text classification tasks, where each unique word in a document becomes a feature. This can result in datasets with thousands or even tens of thousands of features. Many algorithms struggle with this kind of complexity, but naive Bayes handles it effortlessly, leveraging its independence assumption to simplify computations without losing accuracy. Finally, robustness to irrelevant features gives naive Bayes an edge in noisy datasets. Not every feature in a dataset is equally important. Some might even be completely irrelevant. Naive Bayes naturally filters out the noise by focusing on the most significant predictors. This characteristic allows it to maintain accuracy even when the data contains redundant or distracting information. But while these advantages make naive Bayes a powerful tool, they also come with limitations. The independence assumption, for example, simplifies the model, but may not always align with real-world data where features are often correlated. Nonetheless, its simplicity, speed, and reliability ensure that naive Bayes remains a go-to solution for many classification problems. So, as we move forward, it's worth considering not just what this algorithm does well, but also how to work around its constraints to unlock its full potential. Let's explore further. While naive Bayes classifiers boast a range of strengths, they aren't without their limitations. It's important to understand these drawbacks to make informed decisions about when and where to use this algorithm. Like any tool, it shines in certain contexts but falters in others. Let's unpack these challenges. First, the naive assumption of feature independence. This is the cornerstone of naive Bayes' simplicity, but it's also its Achilles heel. The algorithm assumes that all features are independent of each other, given the class label. In real-world scenarios, however, features are often correlated. For instance, in a medical diagnosis task, symptoms like fever and fatigue are rarely independent. They're typically linked through an underlying condition. When these dependencies exist, the independence assumption can lead to suboptimal predictions, as the model cannot capture the interplay between features. Next, there's sensitivity to data quality. Naive Bayes relies heavily on the quality of the data it's given. If the data contains noise, outliers, or imbalanced class distributions, the model's performance can degrade significantly. For example, in a dataset where one class is vastly underrepresented, naive Bayes might struggle to learn its characteristics and produce biased predictions. Similarly, noisy or inconsistent data can skew the probability calculations, leading to misleading results. Another challenge is handling continuous features. While Gaussian naive Bayes can model continuous data by assuming a normal distribution, this assumption doesn't always hold true. Real-world continuous data often deviates from the bell curve, and when this happens, the model's predictions may lose accuracy. Discretizing continuous data is an alternative, but it comes with trade-offs such as potential information loss and increased preprocessing complexity. These limitations don't mean naive Bayes isn't a valuable tool. It absolutely is, but its performance is highly dependent on the nature of the data set and the problem at hand. When features are strongly correlated or when data quality is poor, other algorithms may outperform it. However, in cases where its assumptions hold reasonably well, naive Bayes can deliver fast, reliable results with minimal computational overhead. The takeaway is this: knowing when and how to use naive Bayes is just as important as understanding how it works. By recognizing its strengths and limitations, you can leverage it effectively while being mindful of the situations where it might struggle. Up next, we'll explore how to balance these trade-offs and unlock the full potential of naive Bayes in practical applications. Let's keep going. The true value of naive Bayes lies in its versatility and real-world applications. It's not just a theoretical concept, it's a workhorse for some of the most practical problems in machine learning. Let's dive into how this algorithm powers a range of solutions across industries. One of its most well-known applications is spam detection. Email services rely on naive Bayes to classify messages as spam or not spam. By analyzing features like the frequency of certain words or phrases, naive Bayes calculates the probability that an email belongs to either category. Its simplicity allows it to achieve high accuracy rates, often exceeding 95%, by leveraging the conditional probabilities of word occurrences. This speed and effectiveness make it ideal for processing millions of emails in real time. Another critical use case is sentiment analysis, where naive Bayes helps companies understand customer feedback. Whether it's analyzing reviews, tweets, or social media posts, the classifier determines whether the sentiment expressed is positive, negative, or neutral. Businesses use these insights to gauge public opinion, improve customer satisfaction, and refine their strategies. Its ability to process large datasets quickly makes it a go-to choice for handling high volumes of text data. In healthcare, medical diagnosis is another domain where naive Bayes excels. It assists in predicting diseases by analyzing patient symptoms and medical history. By calculating the likelihood of various conditions, the algorithm helps healthcare professionals make informed decisions. Its probabilistic foundation ensures diagnostic accuracy, ultimately enhancing patient outcomes and reducing diagnostic errors. Naive Bayes is also a cornerstone for document classification. Whether categorizing news articles, research papers, or legal documents, it efficiently sorts content into predefined categories. Libraries, content management systems, and online platforms rely on it to organize information and improve retrieval. Its ability to handle high-dimensional feature spaces makes it particularly well-suited for text-heavy applications. Lastly, recommendation systems harness the power of naive Bayes to personalize user experiences. By analyzing user behavior, preferences, and interactions, these systems suggest products, services, or content that users are likely to enjoy. This not only enhances user engagement, but also drives sales by providing tailored recommendations based on past data. From spam filters to personalized recommendations, naive Bayes proves its worth across a wide array of fields. Its efficiency, simplicity, and effectiveness make it a reliable choice for solving classification problems where speed and scalability are key, but as we've seen, its strengths come with certain limitations, which makes understanding the nuances of its applications all the more critical. Let's move ahead and explore how it compares to other algorithms and where it fits into the broader landscape of machine learning. When choosing a classification algorithm, it's natural to compare naive Bayes with other popular models to understand its strengths, weaknesses, and where it fits best. One of the most common comparisons is between naive Bayes and logistic regression. While both are widely used for classification tasks, they have key differences that impact their performance in different scenarios. Naive Bayes is fast, simple, and effective, especially for high-dimensional data. It assumes that all features are independent given the class label, which simplifies probability calculations and allows for rapid training. This makes it particularly well suited for text classification tasks such as spam detection or sentiment analysis, where thousands of words act as individual features. Even with its strong independence assumption, it often performs surprisingly well because real-world data sometimes aligns well enough with its assumptions. Logistic regression, on the other hand, is a more flexible and powerful model in cases where relationships between features matter. Unlike naive Bayes, logistic regression does not assume independence between features. Instead, it models the relationship between input variables using a logistic function and estimates probabilities based on a linear combination of these features. This makes it more robust in situations where dependencies exist among features, such as in medical diagnoses or financial risk assessments. One of the key advantages of logistic regression is its interpretability. The coefficients assigned to each feature provide insights into their impact on the classification decision. This transparency is valuable in fields like healthcare and finance, where understanding how decisions are made is just as important as the accuracy of predictions. In contrast, naive Bayes relies on probability calculations that can sometimes be harder to interpret in a real-world context. However, naive Bayes often outperforms logistic regression in cases of small data sets or when data is sparse, such as text classification problems. Logistic regression, while powerful, requires more data to generalize well and can struggle when training on limited samples. Additionally, logistic regression is computationally more expensive than naive Bayes, especially when dealing with very high-dimensional data sets. The choice between the two ultimately depends on the problem at hand. If you need a quick, scalable, and efficient solution, naive Bayes is a solid choice. If you have enough data and need a model that captures relationships between features without strong independence assumptions, logistic regression is often the better fit. But naive Bayes isn't just compared to logistic regression. There's another major contender: decision trees. In the next section, we'll see how naive Bayes stacks up against decision trees and when one might be preferred over the other. Let's keep going. When choosing a classification model, another common comparison is between naive Bayes and decision trees. While both are widely used in machine learning, they take fundamentally different approaches to classification. Understanding their differences can help in selecting the right model for specific tasks. One of the key distinctions between the two is how they handle data types. Naive Bayes is particularly effective for categorical data and text classification, where probabilities can be calculated based on feature occurrences. However, it requires additional preprocessing when dealing with continuous data, often assuming a Gaussian distribution to make predictions. Decision trees, on the other hand, are more versatile, as they can naturally handle both categorical and continuous data without the need for preprocessing. Instead of relying on probability calculations, decision trees split the data at each node based on feature importance, making them highly adaptable to different data types. Another major difference lies in interpretability. Decision trees offer a clear, visual representation of decision making. Each split in the tree represents a decision rule, making it easy to trace how predictions are made. This is why decision trees are often preferred in domains where transparency is important, such as finance and healthcare. Naive Bayes, while mathematically elegant, lacks the same level of interpretability. It calculates probabilities based on Bayes' theorem, and while the final prediction is clear, understanding exactly why certain decisions are made can be less intuitive. Performance and assumptions also set the two apart. Naive Bayes is fast and computationally efficient, even for very large data sets because of its strong independence assumption, treating each feature as unrelated to the others. However, this assumption doesn't always hold true in real-world data, potentially leading to inaccuracies when features are highly dependent. Decision trees, on the other hand, do not require such assumptions and can capture complex relationships between features. They are particularly strong when patterns exist in the data that involve interactions between variables. However, decision trees come with their own limitations. They are more prone to overfitting, especially when they grow too deep and become overly complex. While pruning techniques can help mitigate this, decision trees often require more tuning and optimization than naive Bayes. Naive Bayes, in contrast, is much more resistant to overfitting, particularly in cases where the data is sparse or high-dimensional, making it an excellent choice for text classification and NLP tasks. Welcome to the new era of video creation with Jog AI. Simply type your script to get started. Now it's time to move from theory to practice, implementing naive Bayes in Python. Understanding the mathematical foundations is crucial, but applying the model to real-world data is where the real power of machine learning comes to life. The great news? Naive Bayes is one of the easiest classifiers to implement, thanks to its simplicity and efficiency. Let's walk through the step-by-step process. First, it all begins with importing the required libraries. In Python, we rely on well-known packages like NumPy, Pandas, and scikit-learn. NumPy helps with numerical computations, Pandas handles data manipulation, and scikit-learn provides all the tools we need to implement and evaluate naive Bayes. Once the libraries are in place, the next step is to load and preprocess the dataset. Data preprocessing is critical, as naive Bayes requires clean, structured input. This means handling missing values, encoding categorical variables, and normalizing or discretizing continuous features if necessary. Whether it's text classification or numerical data, proper preprocessing ensures that the model performs at its best. After preparing the data, it's time to split it into training and testing sets. This is where train test split from scikit-learn comes in. By dividing the dataset into a training set, typically 80%, and a testing set, 20%, we can ensure that the model is trained on one portion of the data while being evaluated on unseen samples. This step prevents overfitting and helps assess real-world performance. Now comes the key part, training the naive Bayes model. Scikit-learn provides different naive Bayes implementations depending on the type of data. For text and categorical data, Multinomial NB is used. For binary features, Bernoulli NB is the best fit, and for continuous data, Gaussian NB models the normal distribution. With just a few lines of code, the model is trained and ready to make predictions. Finally, the trained model is used to make predictions and evaluate performance. The predict function generates classifications for new data points, and evaluation metrics such as accuracy, precision, recall, and F1 score help determine how well the model is performing. The confusion matrix provides insights into false positives and false negatives, highlighting areas where the classifier excels or struggles. And just like that, naive Bayes is implemented. The entire process, from data preprocessing to training and evaluation, happens in seconds, making it one of the fastest and most efficient classifiers available. But the real question is, how well does it perform in practice? What do these evaluation metrics really tell us about its strengths and weaknesses? Up next, we'll break down model evaluation, analyzing how to measure and interpret naive Bayes' performance in real-world applications. Let's keep going. Evaluating a machine learning model is just as important as training it. A classifier is only as good as its ability to make accurate and reliable predictions, and with naive Bayes, performance evaluation helps us understand its strengths and weaknesses. But what metrics should we focus on? Accuracy alone doesn't always tell the full story, especially in cases of imbalanced data sets. That's why we look at a combination of different evaluation metrics. The first and most commonly referenced metric is accuracy, which measures how many predictions were correct out of the total predictions made. It's a great starting point, but can be misleading in datasets where one class is much more common than another. For example, if a model classifies 95% of emails as not spam correctly, but misses 50% of actual spam messages, the accuracy might still seem high, even though the model isn't doing a great job at detecting spam. To get a clearer picture, we use precision. Precision is the ratio of correctly predicted positive cases to all predicted positives. In other words, it tells us how many of the emails classified as spam were actually spam. This metric is crucial in scenarios where false positives are costly, like in medical diagnosis, where predicting a disease when it isn't present could lead to unnecessary treatment. Then there's recall, also known as sensitivity. This measures the model's ability to find all the actual positive cases. In spam detection, recall tells us how many of the real spam emails the model successfully identified. A high recall means fewer false negatives, which is essential in tasks where missing a positive case can have serious consequences, such as detecting fraudulent transactions. Since there's often a trade-off between precision and recall, we use the F1 score, which is the harmonic mean of both metrics. The F1 score balances precision and recall, making it a more reliable measure of performance when one metric is significantly higher than the other. Finally, one of the most insightful evaluation tools is the confusion matrix. This matrix shows the breakdown of true positives, true negatives, and false negatives, giving a more detailed view of the classifier's performance. By analyzing the confusion matrix, we can pinpoint exactly where the model is making mistakes and adjust accordingly. Together, these metrics provide a well-rounded assessment of naive Bayes' performance. They help us move beyond simple accuracy and understand how well the model balances the need for precision and recall. But even the best models need optimization. So how do we improve naive Bayes' performance further? Up next, we'll explore hyperparameter tuning, feature selection, and other techniques to refine and enhance this classifier. Let's dive deeper. Even though naive Bayes is a simple and efficient classifier, there's always room for improvement. Fine-tuning the model can make a significant difference in performance, especially when working with complex datasets. This is where hyperparameter tuning and feature selection come into play, helping the model generalize better, reduce errors, and improve classification accuracy. One of the most effective ways to refine naive Bayes is through hyperparameter tuning. While naive Bayes doesn't have many parameters to tweak compared to other models, one key parameter that can make a difference is Laplace smoothing, also called additive smoothing. In real-world datasets, we often encounter unseen features, words in a document classification task that never appeared in the training set. Without smoothing, naive Bayes assigns a probability of 0 to these unseen features, which can drastically affect predictions. Laplace smoothing helps prevent this by adding a small value to all feature probabilities, ensuring that no probability is ever exactly 0. Grid search and random search techniques can be used to systematically find the best smoothing value for the dataset. Another way to improve performance is feature selection, which focuses on identifying the most relevant features while discarding the ones that don't contribute much to classification. In high-dimensional datasets, like text classification tasks with thousands of words, not every feature is equally important. Some words carry more predictive power than others. Techniques like chi-squared tests or recursive feature elimination (RFE) can be used to rank features based on their importance and filter out the least useful ones. Removing irrelevant or redundant features not only improves accuracy, but also speeds up model training. In some cases, dimensionality reduction techniques like principal component analysis (PCA) can help simplify the feature space by capturing the most important patterns in fewer variables. While PCA is more commonly associated with numerical data, similar techniques can be applied in text classification to reduce noise and improve classification accuracy. Ultimately, model optimization is about balance, keeping the model simple while improving its ability to generalize to new data. Overfitting, where the model becomes too tailored to the training data, can lead to poor performance on unseen data. Underfitting, where the model is too simplistic, can miss key patterns. By carefully tuning hyperparameters and selecting the right features, naive Bayes can be pushed to deliver even stronger results. Now that we've seen how to optimize the model, The next step is to apply it to a real-world scenario. Let's put it to the test in a case study where naive Bayes is used to tackle a specific problem and measure its impact in action. Let's move forward. Now it's time to see naive Bayes in action with a real-world case study, spam detection. This is one of the most widely known and practical applications of naive Bayes, where the algorithm classifies emails as either spam or not spam based on word patterns, frequencies, and probabilities. Given its speed and efficiency in handling large text datasets, it's no surprise that naive Bayes has been a backbone of spam filtering systems for years. The process begins with data pre-processing, an essential step in preparing raw email data for classification. Before the model can make any predictions, the text must be cleaned and structured. This involves removing HTML tags, special characters, and stop words. Common words like the or and that don't contribute much meaning to classification. Once the data is cleaned, feature extraction techniques like term frequency inverse, document frequency, TF-IDF are applied. TF-IDF converts text into numerical vectors, giving more importance to words that appear frequently in a document but are rare across the dataset. This ensures that words unique to spam emails, like prize or win, carry more weight in classification. Next, the dataset is split into training and testing sets. Typically, 80% of the emails are used for training, allowing the model to learn from labeled examples, while 20% are reserved for testing to evaluate performance. This ensures that the model generalizes well to unseen emails rather than memorizing patterns from the training set. With the data ready, the naive Bayes classifier is trained using the multinomial naive Bayes variant. Since email classification is based on word frequencies, multinomial naive Bayes is ideal as it calculates probabilities based on term occurrences. The model learns which words or combinations of words are most indicative of spam and which are commonly found in legitimate emails. Once training is complete, it's time for model evaluation. The classifier is tested on the remaining 20% of emails to measure accuracy, precision, recall, and F1 score. In a well-optimized setup, naive Bayes can achieve over 95% accuracy, making it one of the most efficient spam filters available. The confusion matrix provides deeper insights, showing where the model correctly identified spam, true positives, where it falsely flagged legitimate emails, false positives, and where it failed to detect spam, false negatives. The success of naive Bayes in spam detection highlights its strengths. It's fast, effective, and scalable to massive data sets. Email providers process millions of messages daily, and naive Bayes enables real-time filtering, keeping inboxes free from unwanted messages. But spam detection is just one example. Naive Bayes has broad applications across industries. What if, instead of emails, we wanted to analyze social media sentiment or product reviews? Up next, we'll look at another real-world case study, how naive Bayes powers sentiment analysis to determine whether people express positive, negative, or neutral opinions online. Let's keep going. One of the most impactful applications of naive Bayes is sentiment analysis, where it helps businesses and researchers understand how people feel about a product, service, or topic. Whether it's analyzing social media posts, product reviews, or customer feedback, sentiment analysis extracts emotional tone, positive, negative, or neutral, using machine learning techniques. Given its efficiency and ability to handle large text datasets, naive Bayes is a top choice for this task. The process starts with data collection. The dataset for sentiment analysis is typically sourced from social media platforms, online reviews, or customer feedback forms. For example, a dataset might contain 10,000 labeled reviews of a product, with each review marked as positive, negative, or neutral. The more diverse the dataset, the better the classifier will perform in real-world applications. Next comes preprocessing, where raw text is cleaned and structured. This involves techniques like tokenization, which breaks sentences into individual words, and stemming, which reduces words to their root form. e.g., running becomes run. Stop words, common but uninformative words like the or is, are removed to focus on meaningful content. Additionally, continuous features may be discretized using binning, ensuring that naive Bayes can work effectively with the processed data. Once the data is ready, it is split into training and testing sets. Typically, 80% of the data is used for training and 20% for evaluation. Since sentiment analysis deals with word frequencies, the multinomial naive Bayes classifier is chosen as it models the probability of words appearing in different sentiment categories. The trained model is then evaluated using accuracy, precision, recall, and the F1 score. In a well-optimized setup, sentiment classifiers using naive Bayes can achieve 85% accuracy or higher, making them a valuable tool for businesses seeking to gauge public perception. The confusion matrix provides further insights, showing how well the classifier differentiates between positive and negative sentiments. The results reveal an interesting trend. Naive Bayes tends to be particularly strong in identifying positive sentiments, but sometimes struggles with nuanced negative expressions such as sarcasm or mixed emotions. This highlights one of its limitations. Since it treats each word as independent, it doesn't fully capture the relationships between words. Despite this, naive Bayes remains a popular choice for large-scale sentiment analysis due to its speed, simplicity, and ability to handle high-dimensional data. Sentiment analysis isn't just useful for businesses. It's also applied in politics, social sciences, and customer service. Companies use it to track brand perception, news agencies analyze public opinion on political events, and customer support teams detect dissatisfaction in real time. But what if we take this concept even further? What happens when we apply naive Bayes in fields with life-changing consequences, like medical diagnosis? That's exactly what we'll explore next, how this classifier supports healthcare professionals in predicting diseases and improving patient outcomes. Let's keep going. One of the most critical applications of naive Bayes is in medical diagnosis, where it helps healthcare professionals make informed decisions based on patient data. By analyzing symptoms, medical history, and other relevant factors, naive Bayes can calculate the probability of various diseases, assisting doctors in identifying potential conditions quickly and accurately. Since medical datasets often involve categorical features, such as whether a patient has a symptom or not, naive Bayes proves to be a highly effective tool in predictive diagnostics. The process begins with data collection, where patient records are gathered from medical databases. A typical dataset may include over 10,000 patient records, containing details like age, gender, symptoms, test results, and previous diagnoses. Feature selection plays a crucial role in ensuring that only the most relevant variables, such as key symptoms and risk factors, are used for classification. Once the data is collected, it undergoes preprocessing to ensure accuracy and consistency. Missing values are handled through imputation, where missing medical details are filled in based on statistical patterns. Categorical variables such as smoker in a yes-no or family history of disease or present-absent are encoded into numerical form. If continuous features such as blood pressure or cholesterol levels are included, they may be transformed or discretized into categorical bins for better compatibility with certain naive Bayes variants. With clean data, the dataset is split into training and testing sets, typically in a 70-30 ratio. Since medical diagnosis involves a mix of categorical, binary, and continuous data, multiple naive Bayes models may be used in combination. Gaussian naive Bayes for continuous variables like blood pressure levels. Bernoulli naive Bayes for binary symptoms, e.g., fever present or not. Multinomial naive Bayes for categorical features, e.g., severity of pain classified into mild, moderate, or severe. Once the model is trained, its performance is evaluated using accuracy, precision, recall, and F1 score. Recall is especially crucial in medical applications, as failing to detect a disease, false negative, can have serious consequences. A confusion matrix helps assess whether the classifier is correctly identifying positive cases while minimizing false negatives. With proper tuning and a well-structured dataset, naive Bayes can achieve over 85% accuracy in certain diagnostic tasks, making it a valuable decision support tool. However, since the algorithm assumes feature independence, it may struggle with cases where symptoms are correlated, such as how fever and body aches often occur together in viral infections. In such cases, more complex models like decision trees or neural networks may be combined with naive Bayes for better predictive power. Despite its limitations, naive Bayes plays an essential role in early disease detection, risk assessment, and clinical decision support, improving the efficiency of healthcare professionals. It's used in real-world applications like cancer screening, heart disease prediction, and detecting infections based on patient symptoms. Medical diagnosis is just one of many areas where naive Bayes proves its versatility. To wrap up, let's take a step back and summarize everything we've explored, its strengths, limitations, and key takeaways. Let's move to the final discussion. We've explored the naive Bayes classifier from its mathematical foundations to its real-world applications, uncovering why it's one of the most efficient and widely used machine learning models. Now let's bring everything together with a final reflection on its key principles, strengths, limitations, and where it fits in the broader landscape of classification algorithms. At its core, naive Bayes is built on Bayes' theorem, allowing it to calculate the probability of a class given specific input features. Its fundamental assumption, feature independence, simplifies probability calculations, making it fast, scalable, and easy to implement. While this assumption may not always hold in real-world scenarios, it often works well enough to produce strong classification results. One of its biggest advantages is its computational efficiency. Naive Bayes can handle large datasets and high-dimensional feature spaces, making it particularly well-suited for text classification tasks like spam filtering, sentiment analysis, and document categorization. Unlike more complex machine learning models, it requires minimal training time and very little parameter tuning, making it an excellent baseline model or a starting point for classification problems. However, like any model, naive Bayes comes with limitations. Its reliance on feature independence can sometimes lead to inaccurate predictions when features are strongly correlated. Additionally, while it performs well in many cases, it may not always be the best choice for datasets with continuous variables unless the data closely follows a Gaussian distribution. In such cases, alternative models like logistic regression or decision trees may provide better results. Despite these constraints, naive Bayes remains a go-to solution for many real-world problems. We've seen how it powers spam detection, sentiment analysis, recommendation systems, medical diagnosis, and beyond. Its versatility, speed, and simplicity make it a valuable tool for data scientists, engineers, and businesses looking for quick and effective classification solutions. So, where does that leave us? Naive Bayes may not be the most sophisticated machine learning model, but its power lies in its simplicity. In many cases, it delivers performance comparable to more advanced models while being significantly faster and easier to interpret. This makes it an essential part of any machine learning toolkit. Now, the real question is, how will you apply naive Bayes in your own projects? Whether you're working on text classification, fraud detection, or predictive analytics, this model is an excellent starting point. If you followed along this far, you're now equipped with both the theoretical understanding and the practical know-how to implement it. Machine learning is all about experimenting, iterating, and optimizing. So why not put naive Bayes to the test in your own dataset? The journey doesn't stop here. The next step is in your hands.